In this video, I'm going to introduce you to setting up a finite element problem using the minimum total potential energy formulation. Now, these terms might be familiar to you already from some fundamental videos that you might have watched on this course or from your bachelor study. So, in general, I would like to break up the entire topic and describe every term independently so that you know exactly how we can set up this potential energy formulation. First of all, let's look at the total potential energy of a system. The total potential energy of a system is basically a complete contribution of the strain energy in the system. So I can write it as the strain energy of the system. And there is also a certain contribution of the work which was done by the external forces. So I'll just write the work external. Now, if you find out the difference between the strain energy of the system and the work done by the external forces, then it gives you a sort of an equilibrium. And this equilibrium is nothing but the total potential energy of the system. Now, if I'll just look at this word now, the minimum. So if I find out the minimum of this total potential energy of the system, then it will correspond to a state of the system in which it is stable. Okay, that means we are going to find out a certain state of displacement in the system, at which displacement this complete total potential energy of the system is still stable. So we will first start by defining all the different terms that we have introduced again now further apart from the total potential energy of the system. And that would be, to start with, the strain energy in the system and then the work done by the external forces. Let's start with the strain energy in the system. When there is a certain load that is applied on a structure, so we just look at a certain continuum and we apply a certain load on it, then because of this external load that is applied, let's call this F, then there will be some kind of a deformation in the system depending on how the load is applied and what are the material properties in the system. Now, when this deformation happens, it's going to cause some amount of energy. And the energy that is generated due to this deformation of the system because of an external load acting on it is stored inside the system in the form of an elastic energy, which is called the strain energy of the system. Okay, so let's look at a more tangible example that we have been following so far. If you remember, we considered a unit cell, and in this unit cell we had a certain displacement because of a force acting here, and there's a certain length, of course, and there was a change in length of delta L. So by considering all the stress strain formulations in the system and finding an equilibrium and defining the stress in the system in terms of the load and the strain in the form of change in displacement per unit displacement, we got to the formulation which said that the force is equal to the stiffness of the system times the change in length delta L. So what I want to do now in this formulation is I want to show you that there is a force applied on the system and there is a change there's a deformation state which happens in the system, and that deformation state is to do with delta L. Now, because of this change in deformation, there is a certain energy generated in the system which will be put into the system and stored there in the form of an elastic energy. So if I release this force and everything is in the elastic region, which is basically linear, then the system should go back to its original form. So I want to do basically some mathematical manipulations. That's it. So some mathematical manipulations will happen now to this formula that I have put here, F is equal to K delta L, and using that we will be able to define the strain energy in the system. Okay, so let's start with the simple term Fk delta L, which you already have here. Now if I say that delta L can be represented as a small change in x as x dash, okay, because the length in this direction is given as x, so a change in this length x is given as x dashed, a small change. And if I want to look at a differential change, even small, a really tiny change, then I can also write it as dx dash. So the equation which we started off with, let's call this equation 1, which we started off with equation 1, we can just replace delta L and then we can write kx dash, right? So if we have the equation F is equal to kx dash already set up, we can now find out what is the energy that is stored inside the system because of a force F acting on a differential length to cause a differential deformation dx dash. Right? So if I say the strain energy of the system or the elastic energy which is stored in the system is actually F dx dash, the integral from 0 to x dash, I will be able to solve it by substituting the value of f from equation 2 to be equal to kx dash dx dash, and by continuously solving it I will get half kx dash square. I can also write this as half kx dash because remember I'm doing some mathematical manipulations to make my point across. Then in that case we can also write for a certain differential volume, we can also write that if the strain energy is given as this, then for a differential strain energy is given as half kx dash, because I can put that inside with the differential length dx dash. So in the in basic idea, what we did is that we took a continuum, we applied a force on it, and there was a certain reaction from the force which was in terms of a deformation. Now this deformation was a differential deformation, so we could find out the differential energy that was spent inside the system. Okay, so with this, let's keep this in mind. This is an important solution that we have here. We're going to use it further. Now let's get to the next part of the derivation. Okay, so we already know that let me just recap this. We defined the differential stored energy to be half kx dash dx dash, and we are every time we work in the finite element formulation, we are always looking at differential volumes instead of differential lengths. So we always start with a volume continuum. So if I just write here on the side that the force is equal to sigma times area, you would most likely agree with me. And if I'm only looking at the axial stress in the x direction, because that was my whole hypothesis with the differential volume here, that this is x and F is acting in x, then the area will be given as a differential in y and differential in z as the length. Dy dz, not the differential, sorry, in this case. So what this basically is just giving us the volume where the load is applied in the system, and the strain epsilon will be very easily given as the differential of x dash and dx, which was the original length. So we can easily write dx dashed as epsilon dx. So this is basic mathematical manipulation. This is not coming from somewhere very special. So dx dash is the small increment in displacement that's happening, and dx is the original length of the domain, because we are looking at everything in a differential format now, not in the continuum format. So if we have now just to replace the terms that are given here, so this was just half of f, if you remember, instead of kx dash, and instead of f, if I can write sigma x dy dz, then I can have the differential stored energy to be given as sigma x dy dz times epsilon dx, coming from both these results. So if I bring everything in a certain order, I will get sigma epsilon dx dy dz, and dx dy dz is nothing but a cube formulation of a volume of length dx dy dz in the 3 directions. So I can write this as half sigma epsilon dB. So having the strain energy which is defined for the differential volume, Now we can actually integrate it over the entire volume to derive the total strain energy in the system, which is under this axial loading that we have provided as an example. So if we define the strain energy for an element, that's why I put this superscript as E for an element, then I have to integrate this energy over a certain volume V. So I'm just going to substitute the result from the previous one, which I'm going to call 4 here. So I will have or most likely 3. I'll keep it 4 because on this page it's easier to remember then. Then I have half of sigma epsilon dV. So I can easily now substitute sigma is equal to E epsilon, which is also something you probably wouldn't argue with me about being correct or incorrect. So I'll continue with that and I will get E epsilon square by 2 dV, which needs to be integrated over volume V of the element. So that is the definition of the strain energy of the system. And if I'm going to consider everything in the finite element domain, then I also know that the volume is going to be made up of a certain number of elements, and these elements will have a certain number of nodes at their vertices. So if I want to write this typically in a elemental format, then the strain energy of the system, of the entire system actually, I would not call it then the element, because that's incorrect. So the total strain energy of the system will be then written as a summation of the strain energy of every element, which basically runs from, I guess, 1 to m if there are m elements in the system. Okay, so that is the derivation of the strain energy of the system. So it's quite simple. You've already seen this before. It's nothing new, but it's good as a recap. Now, if I have a certain system and there is also external work done on the system. So there will, as I mentioned before, the total strain, the total potential energy of the system is defined as the strain energy of the system as well as the work done externally on the system. And the work done externally on the system is nothing but the product of the force acting at every node in the system, as we have already seen before in the finite element formulation. So we can write here that the work done externally, so I will write it as WEXT, can be given as a summation of, let's say, 1 to n, where there are n nodes, of force times displacement at that node. So finally, I can now put all this together and say the potential energy of the system, which is given as pi, is equal to the summation 1 to m of the strain energy of the elements minus the summation 1 to n of Fi ui. So that gives you the total potential energy of a finite element system or finite element discretized system. Now, if you recall, we can go back to the beginning and we said, okay, we want to find out the minimum total potential energy of the system to actually be able to formulate it in the finite element solution method. So, therefore, we would have to find out the minimum. So the minimum potential energy of the system corresponds to a certain state of displacement or deformation in the system when the system is also stable. That means we would have to minimize it for every displacement ui, as we have mentioned here in the external work done. So once we minimize it for every displacement, we will be able to find out the equations which will lead up to the setup of the finite element equation for the system. So coming back here, we need to do a minimization of the total potential energy with respect to the displacement with every displacement in the system. So we can basically do a minimization of the strain energy of the system as well as the work done externally in the system. So this is the framework that I wanted to provide you for the minimum potential energy of the system, how to formulate the components that are present in the minimum potential energy. So starting with the strain energy in the system, the work done which is externally, how the strain energy comes about, how we put it together to form the total potential energy, and for minimizing it so that we can find a state of displacement in which the system is stable, and hence with this equilibrium we can form the finite element equations. So if you now go back to the original steps that we were looking at for a finite element method, then you may remember or recollect now, or even look back in your notes, that the final step before which we can actually formulate the Ku is equal to F equation for linear finite element analysis is always setting up equilibrium. And that is basically if you put this minimized equations together, like a list of equations, because it's going to be minimized for a number of displacements, then we will be able to see a set of equations which, when put together, will lead to the equilibrium equation we solve for a linear finite element analysis of any system. So this is about the basic method. And in the next video, you can follow the same example as we did before, just to set it up so you get an idea of how quickly a finite element formulation can be set up from using the minimum potential energy approach.